So there's tons of different configurations of spectrophotometers, and the most generic one, and also the one that you've used probably most frequently in your career, at least at CC, is this single beam or monobeam type format. And so this is what we've talked about almost exclusively so far, where you have your light source, whatever that might be. That could be a light bulb, or it could be an LED, or it could be a variety of different things. If this is an IR thing, this is a thermal heat source, what we call a glow bar. So you end up having broadband white light, and that goes into this thing called a wavelength selector. So we often just denote that as lambda, which is, you know, another term for that is a monochromator. There's a variety of these things, like a prism. And then we have our sample, which is held by whatever our sample thing is. And then we have light detector, and then whatever our typically they're inside of the computer, there's this thing called an analog to digital converter, which takes an analog signal and converts that into a digital signal. So this is the general layout. The problem here is that this wavelength selector is, you know, it's not automated. This takes forever because you've got this polychromatic light source, and then you've got a wavelength selector, which is allowing a single light frequency to pass through, or wavelength to pass through at any given moment in time. And that's what you had with the Spec 21, which is, or Spec 20, which is this device here. So, you know, if you remember this thing, the sample compartment was right here. So this is where you would drop your cuvette into, and then you would typically measure a blank, which then you adjust this for 100% transmittance or zero absorbance by adjusting the zero adjust. That just literally moves the needle until it's zero. That's blanking your system. And then it has this thing called a wavelength selection. And that wavelength selection is this wavelength selector step. And on this dial here, you'll see a scale that allows you to select in units of nanometers the different frequencies of light or wavelengths of light that you are going to allow to pass through. But that's a physical knob. So that means if you want to collect a full spectrum for full absorbance spectrum, that's going to be absorbance on the Y as a function of the wavelength. And for visible light, this is typically from probably 400-ish nanometers up to about 800 nanometers. So what that would mean is that you would crank this dial all the way down to 400, pop your sample in there, pop the blank in there, zero it, go to 400, and then measure what the absorbance is. That's a single data point. Then you'd remove, you know, redo this blank sample wavelength selection 401, and then you get a number. And you keep doing that cycle every time up through 800 nanometers. If you're doing this at every nanometer, or better yet, at every 1/10 of a nanometer, you're doing this 4,000 times, right, to affect what the overall absorbance spectrum is for your sample. This type of monobeam or single beam spectrophotometer source works really well if your singular goal is to use Beer's law to quantify a concentration of sample, because in that case you're measuring the absorbance at a constant, at a singular wavelength, typically associated with whatever the lambda max is, the wavelength at which maximum absorption occurs. And that's usually predetermined for you. So we just tell you, hey, measure the absorbance at 550 nanometers. And so you set your dial on your wavelength adjuster here to 550, and you measure everything the same, which means you can blank your system once and then just keep measuring all your standards and your samples, etc. That works great. That means that your epsilon here, your molar absorptivity, is also wavelength specific. That's the molar absorptivity at that particular wavelength. The path length is typically 1, and then you can solve for the concentration of your sample. That works really well in a single beam format. But if you want to collect a full absorbance spectrum, which we often do, this is routine, this is a really cumbersome method. Of course, you could go in here and say, all right, well, maybe I add an extra level of sophistication here, and I build a motor and a gear system inside of this thing that steps through my wavelength selection knob at every nanometer, and then somehow has a triggering option so that it only is measuring or collecting the detector signal to the computer at specific intervals, timed to be in sync with our wavelength selection. We can certainly do that. But even in that case, we would call that a scanning spectrophotometer, and it's still not wonderful because you're still collecting at every single step along the way. You're collecting one of those data points, but it's still better. At least it's automated. So this sort of single beam has two major drawbacks. One, it doesn't measure, we don't need to use P naught, I naught, which is the blank, doesn't measure that directly. So no I naught directly. That's an issue because that means we have to blanket for every wavelength. Every single time we change the wavelength, we need to reblanket. That's not built into the system to measure that directly. So that becomes also enormously cumbersome because even if you automated this with a scanning option, it doesn't fix the fact that you don't, you're not collecting it at every point. That doesn't mean that you couldn't just, collect a full intensity spectrum for your sample and then a separate intensity spectrum for your blank, which would be I naught, and then divide them to get your actual absorbance, which is exactly what you're going to do or already have done for your smartphone spectrometers. Totally reasonable. But it's not ideal, and I'll tell you why here in a second. The issue is that you still have to physically remove your blank cuvette and your sample cuvette. And what that does is it just presents more opportunity for error. So the second is the physical removal of cuvettes to collect your actual absorbance. There's really no way around that. Even if you have a scanning system, that still takes you a while. You still have to collect two overall spectra in series, which means you have your blank cuvette, and then separately you have your sample cuvette. They could be the same thing, but you're still picking it up, pulling it out. What that does is it presents an opportunity for presenting error to the system, because if you rotate this thing 90 degrees, you don't remember, there may be microscopically different thicknesses of glass, and if you're normalizing to that, that's a pretty big effect. You could put a fingerprint on this. You could accidentally dilute your sample or your blank because you had a couple residue drops after you rinsed out your blank, then you put your sample in. This is only 3 mils, so even a few drops is going to change that within significance. There's lots of issues, right? If we want to think about this analytically, that the single beam setup is not ideal. It's perfect, as I mentioned, for this type of analysis when the precision and the accuracy required of your calculation of concentration is not held to high standard. And that's why we use them in like a general chemistry course. Okay, so to remedy some of those problems, we can switch to a dual beam configuration, which is much more common in research grade UV-Vis spectrometers, which we have. The general premise for how this works is it sort of just duplicates the original single beam into two. And so you just have two of everything. But what that allows you to do is have your blank fixed in place in its compartment, and you're reading the blank at that given moment in time. And it also has the sample. And so at any given wavelength, we're measuring simultaneously I naught and I at the same time without having to remove stuff. At the same time, we mentioned way back in chapter 5 this thing called instrument drift, if you remember. Remember, this is just a light bulb, which it takes time to warm up, and also it dies over time as the tungsten inside starts to evaporate. And so if you have this thing on, maybe you just flip the thing on right away in the morning, and then you start to proceed to measure samples right away. This thing is still coming up to heat. It may take 30 to 60 minutes to reach an equilibrium, in which case, if you were to do this with a single beam setup, and measure at one point in time you measure your blank, and then later you measure your sample, you're measuring those at different power densities, which means the I and the I naught are not reflective of each other. And so that's going to lead to a huge error. But think about that in the dual beam setup. doesn't really matter because if this thing is at a cooler temperature and it's not really heated up, you're still measuring these two things simultaneously. So when you want to compute the transmittance as the intensity over the full intensity with the blank, doesn't matter. These two things are measured simultaneously in time. So that instrument drift component doesn't change things. The same goes if you leave this on for a day and you start to deal with lifetime issues of the bulb. So it starts to emit weakly, meaning that the overall intensity that's emitting is lower. If you calibrated early in the morning, you ran your blank early, and then in the afternoon you wanted to run this again in the dual beam setup, it wouldn't matter as much. So the dual beam setup is nice. The downside of the dual beam setup is that it's expensive because you've got two of everything. You've got two monochrometers, which turn out to be one of the most expensive parts of spectrophotometer, and you've got two detectors. And this setup doesn't matter. You can leverage a single source, and that's really the bonus here. Is you're using one source and then you're using mirrors to redirect the beam, but it's not the best. It's a reasonable option, but not many people manufacture things like this anymore. This was sort of a stepping stone. Okay, so the sort of more modernized and sophisticated version of the dual beam spectrophotometer is shown below. We call that the modulated dual beam setup, and this is what we actually have at CC. So it's not drastically different, but let me walk you through the steps. So you still have a single light source, but in this case, you've only got a single wavelength selector. So that decreases price considerably, and also notice you've only got a single detector. But we still have both the blank and the sample being run simultaneously. How do we do that? Well, we use this thing called a chopper. And this is sort of a combined type of chopper. There's different choppers out there. This is a combined chopper where it's both a chopper and a mirror. And so what happens is light comes through here of a particular wavelength after it leaves the monochrometer, and then it passes through this wheel. So this thing is of course rotated 90 degrees so that the light is passing through this. Wherever it's white, that's a transparent slot, and then the black line just proceeds directly through the blank sample, and then it goes through this what we call a silvered mirror or a half silvered mirror, which allows the light to pass through if it's at this incidence angle, but if it's at the incidence angle with the green beam path, then it actually causes that to reflect and collect at the detector. So as this chopper is hooked up to a motor that's moving this wheel at a particular frequency that we know, and will cause this thing to rotate in time, and anytime it hits the black region, that's actually a mirror. And that mirror is going to reflect this thing downward to this other alternative beam path off this mirror and then through our sample, off another mirror up to that beam splitter where the two beams are recombined at the detector. So what does this actually look like in practice? Well, this thing is moving at maybe 20 or 30 hertz, so it's rotating really fast, and what you're getting are two beam paths that are superimposed on each other, where when this one's on, this one's off, where this one's off, this one's on, but they're oscillating about 30 times a second, pretty fast. And what that does is it allows us to generate a signal at the detector then that where we have, let's see, the signal, say, from the blank, which is I naught, that's at a maximum at this time point, and then it goes down to, we'll just say 0 is here just so that we can see this, and then it goes down to 0 as it's being blocked by the chopper, and then it goes back up again, and then it goes back down again, and this keeps oscillating at whatever the frequency of the chopper is set to. And sort of the opposite then, the green beam is going to be off or 0 whenever the intensity of the blank is on. This is the sample signal, and then it's going to increase, and it's going to decrease, and it's going to be in opposition to our blank signal. And I'm also not running it all the way up to the maximum here because presumably the overall amount of energy transmitted on the green line is going to be less than that of the blank because that's some amount of that's being absorbed by the sample. So as long as we know this frequency, what we can do is we can actually just tell the computer only look at the signal at the same frequency that this thing is moving. This requires another piece of equipment, which we don't need to go into in this class, but you might in a Chem 342 class, called a lock-in amplifier. And a lock-in amplifier, all it does is it takes a particular weak signal, which would be this, and it amplifies it. And so we can say, all right, monitor only signals at 30 hertz. And what it's going to do is lock into that 30 hertz signal, and it's going to amplify it. And so what we'll end up with is a signal that looks like this as a function of time, where instead of it modulating up and down and up and down, we're only monitoring that particular frequency. So it's essentially a static line. It's not changing. And what we end up with are two signals, one coming that are superimposed on each other simultaneously. One where we have the blank signal and one where we have the sample signal. And so we get these two signals, we divide them inside the computer, and we get in real time a transmittance or an absorbance. Typically that computation is done for us. And the cool thing about that is it requires half the equipment. It requires this special chopper, which is not that expensive, but only a single monochromator and a single detector and a single light source. And any change that we make to one, it's reflected in real time as if it were a true dual beam experiment. And so this is sort of this clever hack. I'm going to show you a quick video for how this works if it's still not intuitive for what's actually happening with the chopper. Hopefully that'll elucidate things. So this is actually a tutorial video or like a sales video from one of the preeminent manufacturers of lock-in amplifiers. This is what everybody uses. They're from Stanford Systems. And so I'll let them walk you through it. But you can see the chopper here in the back. It looks just like the picture, the cartoon that I showed you. Down below, this big unit here is the lock-in amplifier device, and the small unit right here is the motor that controls the frequency.
I'm Ian Chan at Stanford Research Systems. This video will show you how to use an SR865 lock-in amplifier to phase lock an optical chopper to the lock-in amplifier. Let's set up the SR540 chopper controller. We're going to use the 6-slot blade in this video, but the setup works equally well with the 30-slot blade. For the 6-slot blade, we have to use the 400 Hz setting. We also want the reference to output F.
So you can see how the chopper is moving. I'm not going to show you the entire tutorial video because it's irrelevant to this class. But this would be how you would set up your own chopped system. And so if you go on, you do some research, and that research has to do with spectroscopy. Most often the type of spectroscopy you're doing is something you built yourself, not an off-the-shelf system. So if you look at the UV vis, the dual beam UV vis setups that we have in the department, this whole unit plus the lock-in amplifier, they're all built into the UV vis. You don't see all these peripheral components. These would be components if you had a big optical table with a bunch of holes on it and you're mounting all the mirrors and lenses, your light source, etc., and you're building your own device. This is when you would use a setup like that. So looking at the modulated dual beam setup, I want to give you one additional small change. It's still considered modulated, but is even simpler here. And this is actually, if you go to take Chem 342 with me, I have a week-long lab where you'll actually build your own modulated, not dual beam, but essentially dual beam spectrometer. And what you can do is what we would do in a Chem 342 class is you'd spend like 4 days learning circuitry really fast, and you would take a breadboard, and on that breadboard you'd wire up this whole thing, lots of circuits, and that circuit would then wire to your light source. In this case the light source is an LED, but it could just as well be anything. LEDs are nice because they have fast response times rather than an incandescent bulb, which takes time to warm up. And what you can do is build this thing called an oscillator circuit. And what the oscillator circuit does is it essentially replaces the chopper. You no longer need it because what it does is it pulses the LED at a particular frequency. And so we pulse that LED at roughly 1,500 times a second. So you've got this little green LED, and you're pulsing it based on your oscillator circuit at about 1500 hertz. That's way too fast for the eye to see. We can see up to maybe a little beyond 60 hertz, but after that it looks like a continuous beam. So it looks like the LED is just lit all the time, but it's not. It's pulsing. And so then what else you do is you build onto this same breadboard, or another breadboard is your detection circuit. And then on that detection circuit you wire all this stuff up. That's what it looks like. And then you have the light hit this detector, which is a little photodiode, which is essentially the singular component that goes into like a photovoltaic. So it's made of a PN junction of silicon, and that just changes the overall voltage reading that you measure. But remember, you're measuring essentially a pulse of light 1500 times a second, and so the signal that you get is this very rapid pulsing that pertains to the pulsing frequency that's constructed in your oscillator circuit. And so that's not a very useful signal unless you can lock into it. And so what you would do in a Chem 342 class, and the reason why you construct it is not only to potentially build it as a dual beam circuit, but also, and I think this is an important concept, intuition to think about, when you're measuring this stuff, you're measuring it in a lab. What is above you in a lab but these big fluorescent tube circuits? So you've got this fluorescent light tubes, and you maybe never really thought about these things, but they're emanating light down on you. Turns out that those things are not emanating light in a way that's continuous like a bulb would be, but they're actually oscillating based on the AC frequency of the American system, which is 60 hertz. So light, and that's why I was saying we can't really perceive it, most fluorescent lights are pulsing at 60 times a second. Even though they look like a static light above us, they're not. So what that means is your detector that's sitting on this circuit is getting light from the fluorescent tube and pulses 60 times a second. And so what you have is a superposition of two signals, where you have the light that's coming that you don't want because it's not coming from your spectrometer. That's interference. We want to zap that out. And then you have your actual signal, which is in black here. And so the last thing you do on this detection circuit is you build a passive frequency filter or cutoff filter, which allows you to only allow signals to pass of certain frequency. And so we build this thing called a high pass filter, which only allows this black circuit or the black signal to pass. It squashes the red circuit, and so what you end up with is this circuit that looks like this, and then we do some more post-processing of that and we get this nice signal. So you build this in about a week, but I want to just give you a sense for there's different ways to modulate things. The chopper is this really sort of brute force but simple way that works really well, but pulsing your lamp itself is just as reasonable a way. Your goal is essentially to decouple the two components of the optical path using electronics.